who wants to listen to a disaster? This live stream, the 12th DigiPath Digest, was disastrous due to the collapse of the internet. And no, don't worry, I'm not going to be serving you the disastrous version. The disastrous version is currently on YouTube. And I'm not even going to be sharing this with the Digital Trailblazer mailing list because it was so bad. It was kicking me out. It was cutting off my speech. So for the audio version, I went through the whole thing. It's going to be edited. The audio is going to be polished by AI. Thank you, AI, for helping me out so that you have a lot better listening experience than those who are viewing. And today, AI did not only help me make this podcast episode more listenable, I actually invited 2 AI co-hosts. So if you want to listen to how they performed, can they stay on as official Digital Pathology podcast co-hosts? Listen till the end. The first part is going to be just me, enhanced with AI, better audio. The second part are my 2 AI co-hosts. So let's dive into it.
Learn about the newest digital pathology trends in science and industry. Meet the most interesting people in the niche and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
Good morning, my DigiPath Digest Trailblazers. Welcome to the DigiPath Digest, and let me know if you hear me, because I had trouble before. Hear me out of my own live stream again. Why are you doing this? Why are you doing this to me? And we have already some people. Give me a hi and let me know if you can hear me, because I had this beautiful microphone that didn't want to work today. And I had to change last minute. So I would love you to tell me that you hear me. You should. And I want to tell you something. Yesterday, or like this week, or in general, after reading a certain post that I'm going to show to you, it is recording locally. In case I drop off, I will just upload this. Remember how I always say, oh, people are always asking this at the conferences. Will I lose my job when AI will take over? So I felt kind of strange when I saw this. I know it's cutting off a little bit, but let's just ignore this glitch. And let me tell you about some important things. Dr. Candice True, she's a fellow veterinary pathologist. And if there was anyone that I would think of as the rising star, that's her. She's the rising star of implementing AI in veterinary medicine. I had her on the podcast. This podcast is not yet published, but it's going to be published on October 8th. And she basically trained her own ChatGPT. She teaches on AI, on different AI tools. And there was this post that she posted on LinkedIn telling people that you can now make podcasts out of anything. And you just go to, I'm going to share a different screen. You just go to Google Notebook. What is Google Notebook, Aleks? I'm going to show you what Google Notebook is. It's called Notebook LM, language model, I assume. And you can upload whatever you want, like PDF and other documents, and it's going to create a podcast for you. And I uploaded today's PDF, and I will be including this in the audio podcast version, maybe like in addition to what we will be discussing in the DigiPath Digest, or replacing. So I basically gained 2 podcast hosts. So I wanted to let you know that this was the first moment where I felt, oh, this like podcasting? Do you need real people still? I hope so. And if you are here live, let me know in the chat. And we are going to dive into our DigiPath Digest. I think the internet's glitches are over. We're going to start with hybrid convolutional neural network optimized with an artificial algae algorithm for glaucoma screening using fundus images. And this is from Journal of International Medical Research. The impact factor is 4.046. So the objective was to create a decision support system for retinal fundus image-based glaucoma screening. Screening. And they combined computer vision algorithms with a convolutional network for fundus images and applied faster region-based convolutional neural network and artificial algae algorithm with support vector machine classifiers. And they detected optic boundary, optic cup, and optic disc. And there was a segmentation conducted, and they used 3 fundus image databases. There are different databases for fundus images that they trained it on. And the conclusion was that one of those networks, the AAASVM, which is the artificial algae algorithm with support vector machines, was the best and could be the computer-aided decision support that's going to be useful for optometrists. I like these solutions because, so my touch screen is working, but my pen is not working. It's okay. See, it's time to buy a new tablet. I like this type of imaging that is in vivo imaging, so to say, basically imaging that you can do while you have the patient with you, you have the camera, and you take a picture of the eye, and you can run an algorithm, and basically this can be your computer-aided diagnosis system. And I have 2 super papers for you today. I love them very much because, so the first one, the glaucoma screening, I like because it's not whole slide images. Whole slide images are amazing. You can do computational pathology. You can do a lot of things. Basically, you digitized this glass specimen. You now can use all the computational pathology tools to analyze it, to extract insights, do whatever you want with it. But they're huge. They require a scanner. They're computationally still pretty expensive, meaning they're just big. And I mean, there are methods that don't require analyzing this whole image. There is a streaming of the image where you like stream it like a movie. You don't have the whole movie at a time to watch. You watch piece at a time and you still know what's in the movie. So there are technologies like that. But still, like you need a scanner. You need to digitize the analog glass slide. With static images, in vivo images, first of all, fantastic. Like you can immediately use computational pathology, computation, computer vision. Second, the best thing for applicability, for being able to actually reach the underserved area, are static images. And this is what this paper is about, called Model for Detecting Metastatic Deposits in Lymph Nodes of Colorectal Carcinoma on Digital Non-Whole Slide Images. And I see people joining on YouTube as well. Amazing to have you here. Okay, model for detecting metastatic deposits in lymph nodes of colorectal cancer. This was published in Diagnostic Pathology, Impact Factor 2.6. And the main author, the first author, is Dr. Talat Zera, as she was a guest on my podcast. Whenever this live stream ends, I'm going to link to the podcast with her so that you can learn more about her mission and how she is approaching digital pathology, because she is working in Karachi, Pakistan, which is definitely a country that would be considered underserved area, underserved country. And what happened here, we are talking about colorectal cancer, and this constitutes around 10% of global cancer diagnosis and death due to cancer. Sure. Okay, so colorectal cancer, this is 10% of global cancer diagnosis and death due to cancer. And the study there was a retrospective cross-sectional study including digital images of glass slides containing sections of positive and negative lymph nodes. This retrospective study was taking pictures of glass slides, and there was 165 previously diagnosed cases. They were selected from the hospital, Aga Khan University Hospital, from January 2021 to January 2022. So it was 1 year, and the images were generated at 10x. It wasn't 40x, it wasn't even 20x. It was just done at 10x. I think this was to mimic the pathologist workflow, and they were uploaded to an open source platform, to QPath, and analyzed there. There was a deep learning model. Ensemble was applied to the identification of tumor deposits in lymph nodes. And So we have static images, we have open source software, and we have low magnification. So we don't have huge images. So the computational requirement decreases significantly. And what were the results? The negative lymph nodes detected by AI was 78. We had 165 cases. And out of these, 69 were true negatives. So that was 88% were true negatives, and 11.5 were false negatives. That gives us the sensitivity of 89% and specificity of 83.1. And the odds ratio was 40, with a confidence interval of 16.26 to 98.3. And the conclusion is, though it was a small study, its results were really appreciating, and we encourage more such studies with big sample data in the future. I definitely encourage more of those studies because they are so low barrier to entry for digital pathology, and they can help you leverage digital pathology without huge computational resources. The next paper that we have, it is very dear to my heart because of two things. First, it's about annotations, like making it less cumbersome for pathologists. And the second thing is it comes from the non-clinical safety and pathobiology group at Gilead Sciences in California. Why am I excited about this? Because I'm a toxicologic pathologist. I'm a non-clinical safety pathologist. The first author is Atef Mehrabian. The title is Leveraging Immunofluorescence Data to Reduce Pathologist Annotation Requirements in Lung Tumor Segmentation Using Deep Learning. We are using immunofluorescence data to reduce pathologist annotation requirements. Why do we want to do that? Because annotations is the main bottleneck of training, specifically segmentation models. And we still work with annotations as ground truth. So we motivate pathologists to annotate at scale a lot and have consensus. And the best would be 3 pathologists annotating the same lesion and checking everything. That will not happen because we don't have pathologists who have spare time to do that. But still, that would be ideal for great models, right? So what can we leverage? And actually, I was part of a similar project at my previous company where the computer scientists were leveraging a specific immunohistochemistry stage. Here we are leveraging immunofluorescence, so the technology is a little bit different. But basically, what the group here did, they created a large data set of low-cost, low-accuracy pan-CK, that's cytokeratin-based annotations. So we are talking about non-small cell lung cancer, NSCLC, and pan-CK is a marker that stains epithelial cells. Pan-CK is basically like a lot of different cytokeratins. There is more than just one cytokeratin, and cytokeratin is a marker of epithelial cells. And if you stain those epithelial cells, then basically you delineated the tumor. It is still part of many workflows, even though AI advanced, the models advanced on H&E, you can detect different things, but still delineating manually the tumor on images is a bottleneck, is still part of a lot of AI initiatives where pathologists are doing that. It's boring, I have to tell you. So anyway, they stained with pan-CK, and then they pre-trained a model and determined the minimum required size of the expensive but highly accurate pathologist annotation dataset. So here I have to pause for a second. We are using immunofluorescence, and that is not exactly like the cheapest technique to stain something. It's not easy. It's not just clicking a button and generating this out of thin air. You actually have to do a pretty complicated procedure in the lab. So they did IF, and they compared this to the expensive pathologist time. So here's my things like, okay, yeah, if you don't need to do that pathologist time on top of the IF, then maybe you are lowering cost. So they say it was low cost and low accuracy, but this pre-training was enough to have pretty nice results. And they pre-trained the model and determined the minimum required size of the expensive but highly accurate pathologist annotation dataset. And PanCK pre-training was compared to foundation models, which I would need to know which ones, and but that's okay. We can always go to the paper. Or you can use this a Google language model notebook that I showed you at the beginning that actually can summarize it for us and give us a podcast without me having to do anything other than uploading the file. So PanCK pre-training was compared to foundation models, and various architectures were explored for model backbone. And proper study design and sample procurement for training a generalizable model that captured variations in NSCLC and H&E was studied. This is an important sentence. Proper study design was studied. It's so important. Like study design can make or break your study. And if you have the wrong study design, then the data from your study are useless. So proper study design is key. And the H&E imaging was performed on 112 samples from 3 centers, 2 scanner types, different staining and imaging protocols. This is fantastic because not only H&E is like more stable, it's a chemical stain, and even though it's more stable than immunohistochemistry, immunofluorescence that you have to optimize for image analysis if you want to do it right, there is a domain shift, meaning if you have it in different centers, you scan it with different scanners, the models don't perform so well. So here they did inserted a lot of variability, and that's what happened. So they had those different scanners, and attention unit architecture was trained using a large PanCK-based annotation data set, 68 sample, total area of over 10,000 millimeters square. Honestly, I don't know how much that is, but 68 samples is not that much, but that's okay. Now let's check the results, followed by fine-tuning using a small pathologist annotation as data set. 80 samples, so a lot of samples, but the area was just 200 millimeters. Okay, so we had less samples for PanCK annotations, but the area was 10,000. And here we just have the area is 200 millimeters. So a lot less area annotated by pathologists. And they checked intersection over union between pathologists and the detection of PanCK. Intersection over union is the metric that compares how much 2 different annotations overlap. If they overlap perfectly, that's 1 intersection over union. And if they just touch, then it's almost 0, and that's not good intersection over union. So this is what was checked here. So here we have a first-hand example. What happened if the internet goes down, like digital pathology goes out the window? But I just wanted to thank you so much for joining me. On the audio version, there's going to be me trying out this notebook of the post from Candice Chu, Dr. Candice Chu, that I mentioned at the beginning. She's exploring like all the AI tools that are available. And she found this tool, Notebook LM. From here, Notebook LM. So what I did with this notebook was to put the PDF that we were just discussing into this notebook, and it made a podcast out of it. And the podcast is with 2 hosts, male and female host voice, and it sounds so realistic. They have a conversation. It turns the PDF document that is not written in a conversational style into a conversation. So I'm going to be exploring this in the audio version, and I'm going to share it with you. If you are already on my mailing list, that's fantastic. You're going to get this. If you are not, you can go to digitalpathologyplace.com, download my book, and that's how you end up on my mailing list. And then I can give you all the cool things that I'm exploring about digital pathology literature, and pathology and AI, and all those cutting edge things. And in the meantime, You have a wonderful day, and I talk to you in the next episode. Okay, so here it is, another 11 minutes of AI-generated content. Check it out. I listened to all of it. It includes more than just the 3 papers mentioned previously. I have this PubMed alert set up for 10 papers, so it actually summarizes all 10 papers. But what I'm going to do as a little project, like additional podcast project, I want to take 2 papers and make a separate AI generated podcast out of them. Both of them are open source and they are about topics that are close to my heart that help underserved areas. One is going to be the one by Dr. Talat Zera from Pakistan, Karachi, and the other one is going to be about telepathology in Colombia, which was not included in the previous section, but it is included, the abstract is included in the AI chat of my new AI co-hosts, I guess. I'm going to be experimenting with this. And you let me know what you think. I'm going to be sharing this on social media. So whenever you see it and you have an opinion on, okay, is it good? Is it bad? Anything you think about it, you feel about it. Honestly, today was the first time I felt, oh, AI is going to definitely take part of our responsibilities away, and it might feel strange. So without further ado, welcome my AI co-hosts. I feel like I need to give them a name. So it's going to be Miss H and Mr. E, I guess. H and E are going to be discussing the topics that I tried to discuss. And let me know who's better. Which host do you prefer? Dr. Aleks Żuraw, Miss H, or Mr. E?
Welcome back, everybody, to another deep dive. We always bring you the latest and greatest in AI and digital pathology. And, well, this month is no exception. We've got 10 new research abstracts hot off the presses just this past September.
Yeah, we're really talking about AI that's doing more than just, automating tasks. These algorithms are uncovering hidden patterns. They're giving us insights into these diseases that we've never had before. It's really changing how diagnoses are made and how we think about treating diseases.
It's really incredible. We've got AI teaming up with telepathology to bring those expert diagnoses all over the world. We've got algorithms that are analyzing the shapes of tumors and actually predicting how well patients are going to do. It's really incredible.
Yeah.
There's even a glimpse into how AI is being used to understand really complex conditions like childhood asthma. It's really amazing.
Yeah, it really feels like we're pushing the boundaries of what we thought was possible,
Yeah.
Take the Gloria program in Colombia, for example. They're trying to solve this huge problem. How do we make sure that everybody has access to accurate and timely cancer diagnosis, no matter where they live?
So how are they doing that? That sounds like a really tough challenge.
It is, but they're tackling it head on by using a combination of telepathology, which lets doctors share and analyze images of biopsies remotely, and they're combining that with these sophisticated AI algorithms. And what these algorithms can do is they can identify those cancer cells and even flag areas for the pathologist to review. So even in areas where they might not have the specialized doctors, they can get those expert consultations.
So they're basically bringing the world's best doctors to everybody's doorstep using these virtual tools. I mean, that just seems like it's going to really level the playing field when it comes to healthcare equity.
Yeah, absolutely. And speaking of seeing things in a new light, there's also some groundbreaking research on this technique called label-free multiphoton microscopy. Now, traditional microscopy often uses dyes and labels to highlight specific cells or structures. But that can be time-consuming, and it might even mask some important details.
So this label-free approach, is that about kind of seeing those cells in their natural state?
Exactly. Multiphoton microscopy uses the way that light interacts with tissues to create these high-resolution images without needing those traditional labels. But here's where AI comes in. It can be used to analyze these super complex images, find those subtle patterns, those anomalies that our eyes might miss.
It's like having an AI co-pilot helping us navigate and understand that microscopic world with this detail we never had before. Makes you wonder what breakthroughs are just around the corner.
It really does. And, it's not just about catching things early. Some of these studies are also using AI to analyze the shapes of tumors in ways that could completely change how we predict how well a patient is going to do, their outcomes and how we can personalize those treatments for them.
So we've got 2 studies that focus on lymph nodes and tumor identification. Why are those so important?
Well, when we talk about treating cancer, accuracy is everything. Knowing the exact size and spread of the tumor, especially in the lymph nodes, is absolutely critical for staging cancer correctly. And that staging is what determines those treatment decisions. Do we use surgery? Do we use chemotherapy, radiation? Getting that staging right is sometimes the difference between successful treatment and, a worse outcome for the patient.
So it's really about getting those measurements right down to the microscopic level.
Yeah. It's like having a microscopic ruler.
Exactly.
And the implications are huge. Imagine being able to stage cancer with even more certainty than we can now. That could lead to much more targeted treatments, minimizing side effects and really maximizing how well those treatments work.
So we're really talking about making personalized medicine a reality, and it sounds like AI is a big part of that. But, it's not just about cancer. These abstracts cover a pretty wide range of applications for AI.
Oh, absolutely. AI is not just limited to one area of medicine. We're seeing it being used to analyze those complex patterns in all kinds of diseases, like that study on childhood asthma, for example.
Right. And what's interesting about that one is it shows how AI can work with data that's not even visual, right? Like we're talking about lung function tests, environmental exposures, even genetic information, and AI can put all that together.
Exactly. AI is really good at finding those hidden connections and huge amounts of data connections that we as humans might miss. And in the case of asthma, AI might be able to find those early warning signs or predict when someone's going to have a flare-up or even personalize their treatment plan based on their unique risk factors.
It's like AI is giving us this deeper understanding of the disease itself, not just the symptoms. It's amazing to think about how this could change healthcare on a much larger scale.
Absolutely. Now, there's another study I wanted to touch on that really shows how AI can make pathologists even better at what they do. This one focused on pilomatricoma.
Pilomatricoma, remind me what that is again.
It's a type of skin tumor that's benign, so it's not dangerous, but it's pretty common in kids. And sometimes it can be mistaken for other skin conditions. So that's where the diagnosis is really important. The key is being able to look under the microscope and identify those specific cells, basaloid cells and ghost cells.
And that's where the AI comes in.
Exactly. They used a deep learning algorithm in this study to not only help diagnose pilomatricoma, but to actually highlight those important cells within the biopsy image.
So it's like the AI is giving the pathologist a guided tour of the most important areas to look at.
Exactly. It makes the whole process smoother, improves accuracy, and ultimately means that pathologists can diagnose things faster and with more confidence.
So it's not replacing the pathologist. It's more like giving them a really powerful assistant.
Exactly. And speaking of augmenting expertise, there was that study that used a technique called retrosynthetic saliency mapping. What is that all about?
Yeah, that one sounded really interesting.
Basically, the AI looks at the image and creates kind of like a heat map showing the areas that are most important for making the diagnosis.
So it's like the AI is saying, hey, pathologists, pay really close attention to this area. This is what's key here. It's like giving them X-ray vision for pathology.
Uh-huh. I like that analogy. It really gets at what AI can do. It can help us see things that we might easily miss, even those trained professionals. And that brings up a really important point about data in AI.
Right, these algorithms don't just magically work. They need to learn from data. And not just any data. It has to be high-quality data that's diverse and accurately labeled.
Exactly. And that's actually one of the biggest challenges in the field. A lot of these studies talked about how much work goes into creating these large and robust data sets.
Like that study that used pan-CK-based annotations for segmenting lung tumors. Can you explain what that means?
Sure. So pan-CK is a technique where they use fluorescent dyes to stain different proteins in the tumor. And what that does is it creates this detailed map of the tumor so we can see its borders more clearly. And that helps with segmentation, which is basically outlining the exact boundaries of the tumor in the image.
So it's like giving the AI a much clearer blueprint to learn from.
Yes, exactly. Right. And the results were really impressive. They were able to significantly reduce the amount of manual annotation that the pathologists had to do, which frees up their time to focus on more complex cases.
That's huge. It shows how we can use AI to handle those tedious tasks and really boost efficiency in the labs.
It's all about finding those win-win situations where AI can complement what humans are good at and just make the entire workflow better.
Now, I don't want to get too lost in the technical details, but there was one more study that caught my eye. It talked about using something called immunofluorescence data to make lung tumor segmentation more accurate.
Ah, yes. That study was interesting because it showed how AI can actually combine different types of data to get even better results. So instead of just using those standard images, they also included data from immunofluorescence staining, which, as we talked about before, highlights specific proteins within the tumor.
So it's like giving the AI a more complete picture of what's going on.
Exactly. By combining those different data sources, they were able to create an algorithm that was even more accurate at identifying the edges of the tumor.
And having that level of accuracy is so important for making those big decisions about treatment, like whether or not surgery is even an option or how much radiation might be needed. It really shows how AI can help personalize those treatment plans based on a much deeper understanding of each person's tumor. It's amazing how much information we can get from just one tiny little biopsy image these days.
I know, it's really incredible. And it really speaks to how far we've come in such a short time in digital pathology and AI. I mean, just a few years ago, we could only have dreamed of this level of detail or making these kinds of predictions.
Feels like we're on the edge of a revolution in healthcare here.
Oh,
Like any revolution, there could be challenges that come with all this opportunity.
absolutely. As we go further down this road with AI-driven diagnosis, we've got to keep the ethics in mind. Think about potential biases. We have to make sure that these technologies are developed and used responsibly. We need to always be asking ourselves, are we building systems that are fair? Are they transparent? Are they accessible to everyone? Really, really important questions.
Yeah.
And it makes you realize that this isn't just about the tech itself. It's about collaborating, having these open dialogues, making sure that AI is serving humanity in a way that benefits everybody.
Couldn't have said it better myself.
Yeah.
It's about taking the ingenuity of these algorithms and combining that with the expertise of our healthcare professionals. Because at the end of the day, it's about giving them the tools they need to make the best decisions for their patients. One thing that struck me looking at all these abstracts was just how global this research is. We've got studies from Colombia, from China, from the US. It really highlights how this is a worldwide effort.
It's really encouraging to see because when you think about the biggest challenges in healthcare right now, improving access, personalizing treatments, really understanding these diseases at a deeper level, these are global issues that need global solutions.
Exactly. It kind of gives you a sense of hope, right?
Yeah.
Scientists and doctors from all over the world working together with the shared purpose of using technology to improve human health.
It's a good reminder that even when the world feels divided, science and technology have this power to connect us and drive progress. And these abstracts, they give us this glimpse into a future where location isn't a barrier to quality healthcare.
A future where we're diagnosing these life-threatening diseases faster than ever, tailoring treatments to each individual patient, and really pushing the boundaries of what we thought was possible.
That's the future we're all working towards.
Yeah.
And it's a future I'm really excited about.
As are we. Well, we've covered a lot of ground today. Everything from AI-powered microscopes to personalized medicine to the ethical considerations of it all. And remember, this is just the beginning.
Oh yeah, the field of AI and digital pathology is just exploding right now. The possibilities are really limitless.
So stay curious, keep exploring, and join us next time for another deep dive into the world of digital pathology. Until then, happy diving, everybody.
Okay, it's me back again, your host, Dr. Aleks. What did you think? If you've listened till the end, you are a true digital pathology trailblazer, and I definitely want to hear from you what you thought about the AI-generated content. I think it's impressive, and I will be experimenting with this. I don't know yet how I will incorporate it. It's definitely leverage, and I love tools that give me leverage, and that very much makes me think. So initially, I told you I felt strange about this, but now I'm thinking that AI taking over so many things kind of gives us permission to be unapologetically ourselves. So that's what I'm going to be leaning towards. Let me know what you think about it. Are you scared? Are you excited? A combination of both. It's a combination of both for me, and I'm going to be actively figuring out how to use this tool to leverage the promotion of digital pathology. I'm looking forward to hearing from you, and I talk to you in the next episode.